Today's problem was submitted by a viewer, and it says, a ball is projected with speed u and at an angle of elevation alpha from a fixed point O. The ball moves under gravity towards a smooth vertical wall, which is at a distance d from O. And after impact with the wall, it returns directly to O. The coefficient of restitution between the ball and the wall is E. By equating two distinct expressions for the total time of flight, or otherwise, show that EU squared sine 2 alpha is equal to 1 plus EGD. Okay. So I understand what's going on in the question. Let's draw a diagram to see what's happening. Here's the point O. A ball is shot with a speed of u at an angle of alpha, like this. But then, of course, it continues under the effects of gravity, so it'll have a parabolic path. And then it bounces off a wall. And when it bounces off the wall, of course, it gets reflected like so. And then it says it returns directly to the point O. The only thing that I don't quite understand in the question, and this is probably just because of different terminology, the question says that the coefficient of restitution between the ball and the wall is E. Now, of course, if the ball bounced off the wall with a perfectly elastic bounce, then the speed that it comes off the wall is the same as the speed it goes into the wall. And for it to return to the original point, it would have to hit at a horizontal tangent. And so the path that it takes up would be exactly the same as the path that it takes down. Now, I'm assuming that this coefficient of restitution means that when the ball hits the wall, it reflects off such that the angles are the same. Like it reflects off the way light would. But I guess we have to take the velocity or the speed of the ball and multiply it by some number, which is this coefficient. That's what I assume this coefficient of restitution means, right? Because if the ball is shot up like this, it bounces off with a lower speed. If it bounces off at a lower speed, it can return down to the original point. But yeah. Okay, so how do I want to set this all up? I suppose the first thing I want to do is figure out, for this general speed and direction of the shot and the distance given here, I want to figure out the height of the reflection point and the speed it's traveling when it hits that reflection point and the angle at which it hits that reflection point. Okay, I'm going to draw a new diagram, which is a little bit more, maybe something easier to deal with. So there's the point O. There's this. So this is has a magnitude of u. That's an angle of alpha. Okay. So the horizontal speed is u cosine alpha, and the vertical speed will be u sine alpha minus g times t, where t is the amount of time that passes. Okay, so Vx, so t is going to be the time of reflection. So that says that Vx times t is equal to the distance d. So t is equal to d divided by u cosine alpha. So then the velocity at the time of this at the time of the hit, the y velocity will be u sine alpha minus g d over u cosine alpha. Okay. And what is the height of the reflection? Let's say height is a function of t, and that's going to be the integral from 0 to t of Vy s ds. So the height at time t is u sine alpha t minus g capital T squared over 2. I don't know if we might actually not need the vertical, the angle of incidence or anything like that. We might not need the height either. No, I think we will, but let's continue with this just for now. And I'm piecing some things together in the back of my mind that I'll mention in a second. Oh, so capital T is d over u cos alpha. Okay, so that's the height at time capital T. So here's my thought now. Because of, and I mean, I'm giving a bit of a hint here because of the way the question is worded. By equating two distinct expressions for the total time of flight, show that this relation holds. So the time that it takes to go from here to here is very easy to compute. We have the horizontal component of velocity, and we have a distance, so we can compute how long it takes to go from here to here. And again, I'm assuming that after the ball bounces, its velocity gets multiplied by this constant e, which they're calling the coefficient of restitution. I've never heard this term before, but that seems to be a pretty good, a reasonable assumption for how this works. So then we can compute, given that the velocity on the way back is going to be this times this coefficient of restitution, we can then compute the time that it takes to go back. Fine, very easy. Now I have the height at which the ball impacts, and I can write down the vertical component of velocity also as a function of time, but this will be as a function of time after the bounce. And that will just be, again, take the velocity at the time of the bounce, multiplied by e, and then allow that velocity to continue to change under the forces of gravity. So I have the total time, and then what I want to do is I have the time it takes to go from here and back, but I can compute then also the time it takes to go up to the point of reflection and then down again from the point of reflection. So let's simplify this a little bit. This is equal to d tan alpha minus g d squared over 2 u squared cosine squared alpha. Okay, so let's call it velocity x prime, or hat, to represent after the bounce. This is equal to, and we'll use for the horizontal velocity, we'll use speed. So I don't care about the sign or anything like that. So this will be e times u cosine alpha. And so v hat x times, let's call it t2, is equal to d. So t2 is equal to d divided by eu cosine alpha. So the total time, t1 plus t2, is equal to d over eu cosine alpha plus d over u cosine alpha. So the total time, I'm going to replace these all with t1 to represent the time it takes to get the first travel part. Okay, so capital T is 1 plus 1 over e times d over u cosine alpha. Okay, now v hat of y as a function of t, and now t equals 0. For this expression, t equals 0 represents the time of reflection, so the path is on the way back. So this is going to be equal to e times v of y at time capital T1. No. Minus g t. Yeah, so it's the initial speed, the initial vertical velocity, minus the effect of gravity, or plus the acceleration due to gravity. So the vertical component of velocity at the time of impact this should be, I should write this as Vy as a function at time t1. Okay, I'm going to put a little box around that because I'll need that later. Okay, so the integral from 0 to t2 of Vy hat s ds, that should be equal to negative h. Negative h of negative h of t1. Okay. This is getting pretty messy. Because, you know, it's a bit messy because the when looking at the vertical direction, it's not so easy to write the total, even the individual times of flight. Unless we're going to get like a bunch of cancellation in this expression somewhere. Maybe what I should do is not use the I'm going to write everything in terms of the vertical dimension, but I'm not going to use any of the results about the horizontal dimension. So the vertical speed as a function of t is simply u sine alpha minus g of t, and that's until reflection. Okay, that's the velocity at time t1. Let's say vy hat at t is e u sine alpha minus g. Let's just write this as e vy t1 minus g t. Okay. So the speed gets multiplied by e, but then we continue to subtract the effects of gravity. This is true for t greater than or equal to t1. Okay. And I want to write the total, the integral of this whole thing should be 0. So this equals 0. This is going to be the integral from 0 to t1 plus the integral from t1 to t1 plus t2. That equals 0. Integral from 0 to t1 of u sine alpha minus gt dt plus the integral t1 plus t2 of e times that term Okay. I just don't see how we're going to get a nice expression involving maybe I mean, can I use this to isolate and solve for t1 plus t2 somewhere? So the question says by equating two distinct expressions for the total time of flight, but this doesn't really tell us the total time of flight. This expression, like, unless there's a way to rearrange this to solve for. I need this number, t1 plus t2. Oh, hold on. Hold on. Okay, so again, this goes back to like my interpretation of this coefficient of restitution. Maybe it doesn't affect the vertical. Oh, of course, this is going to be so much easier now. It doesn't affect the vertical velocity. It doesn't affect the vertical velocity, only the horizontal. So essentially, anytime I use this in a vertical dimension, this quantity E should be equal to 1. Oh my goodness, this is so much easier now. In fact, and I can see from the final expression that this is certainly going to be true. So the vertical speed is u sine alpha. And that's so the vertical speed as a function of time is equal to u sine alpha minus gt, and I simply have the integral from 0 to the intersection time of vyt dt is equal to 0. So this says u sine alpha capital T minus g over 2 capital T squared is equal to 0. And so, of course, capital T is equal to 2u oh God, u sine alpha t is equal to g over 2 t squared. So 2u sine alpha divided by g is equal to capital T. Okay, so there's the other expression for capital T. And where was my original one? Here. So let's just copy this. And set these things equal to each other. So this is equal to 2u sine alpha over g. And rearrange, so I have, this is 1 plus e over e times dg is equal to 2u squared sine alpha cos alpha. So 1 plus e times dg is equal to u squared times e. 2 sine cos is the same as sine of 2 alpha, right? Yes. And that is the expression given, right? 1 plus egd is equal to eu squared sine 2 alpha. Oh man, this could have gone so much faster. It makes sense, you know, bouncing off a vertical wall, why would the vertical component of velocity be affected? But yeah, this was just, I don't know, huge misunderstanding on how things working. It's not just a terminology thing. I don't know why I had it in my head that, where's the first place that I used it? Here, the vertical speed after the reflection should not be multiplied by this constant because you're bouncing off of a vertical wall, a smooth vertical wall. Okay, could have gone a lot faster if I didn't take this detour and understood the problem from the get-go in a better way. Yeah. I don't have much more to say about that. I mean, given that this is like some kind of derivation, I'm sure at this point that everything I did, at least the correct parts of what I did, are correct. You know, from here downwards, you know, I end up with the same expression that they're asking for. So, you know, there's not going to be any mistakes once I figured out the proper way to interpret everything in this question. Thanks for the submission, and thanks for watching.